All right, welcome. This is Noisy Neighbors through networking.
Yes. I'm René. You will see me here. I hope you will recognize me after the talk and whatnot. If you have any questions, come later to me.
Hi, I'm Ben Kochie. I'm an infrastructure software engineer at Reddit, but I tend to wear an SRE hat a lot of the time. And yeah, so over the last number of months, we've had some incidents, and there's been a bunch of incidents. And while we call them incidents, they're not typically user visible, or at least they're not really user visible. We have a lot of small incidents because we have fairly tight SLOs on a bunch of our services, especially a couple that we'll be talking about later. Only a very small amount of users are impacted, but it's the long tail. And so this is something you might see as you tighten up your monitoring. You have tight SLOs. This is the fourth and fifth nine in our infrastructure. And yeah, they started to finally go down after we started rolling out some fixes for this for these problems. And so what we're going to talk about is we have a few different cases of similar but not exactly the same problem. And we'll be going through them, and then other thoughts on what will be, what other improvements we can make. What is Reddit shaped? So one of the things that we have to think about is people always say, oh, I have a large scale, or I have a lot of data. And I don't like to talk about large. I like to talk about actual numbers. And so we have 100 million daily active users now, and our large Kubernetes clusters are a reasonable amount of scale when it comes to what a Kubernetes cluster can handle. And it's a lot of multi-tenant, a lot of microservices, different services that are also on their own take up double-digit percentages of the cluster. And there's a lot of traffic going through this cluster. We do somewhere between 500,000 and 1 million requests per second in total, spread across some of these clusters. It's a lot of data. And so we're going to start with the Telegraph case. And I wanted to think about, before we really dig too deep into this, is we want to talk about networking. And I like to, whenever we talk about networking and packets, I have this old internet meme that is, what if Dr. Seuss wrote in software manuals? And so when a packet hits a pocket on a socket on a port, and the address is interrupted, when the bus is interrupted as a very last resort, and the address of your makes your floppy disk abort, then the packet socket pocket has an error to report.
Yeah.
So Telegraph.
Yeah, and I'll take over for a moment, because before we can actually understand what we were just saying, I want to go a bit through in AWS what happens between your network card getting a packet and your process actually being able to process it. So the first thing is, like, the packet starts at the ENI. That one does something really helpful. It hashes it up based on source and destination up to 8 receive queues. The problem here is already that this requires something where you actually have an IP packet with a port, so TCP or UDP. If you're doing any sort of encapsulation like VXLAN or IP and IP, this one has to fall back to a less good hashing basically on the source node. Okay, so we have it on that receive queue. This will fire an IRQ tied to a certain CPU. In this case, I just put up CPU 14 as an example, where we're now in this hardware IQ mode in the upper part of our interrupt handler. That will make sure we're scheduling a soft IRQ where we will start actually putting the packet back onto the softnet backlog. We will get to that actually later on, or we will get to most of the pieces here later on again. And we can start processing the packets, are going through IP tables, routing, TC, BPF, actually multiple times, because we're also going through the different network namespaces up to the point that we're running like the TCP state machine, putting it into a process buffer, where then the process can happily, hopefully read it.
Yeah, so it's pretty complicated to actually get a packet from the hardware into your process. And so in the early days of Reddit, we had, or at least before I joined Reddit, we had a statsd and telegraph-based monitoring stack. And we had started to migrate over to a Prometheus-based monitoring stack, but we still had some leftover services that were still emitting some telegraph packets, packets from their service to a telegraph that would aggregate it and send it to a third-party SaaS. We got rid of that, but we still had the telegraphs in place to receive packets so that there wouldn't be any problems. And so these telegraph instances were just dev nulling the traffic, but it was still there. And so what would happen is a telegraph would, we started seeing some long tail latency in one of our services. And I looked at it and said, oh, that correlates with a telegraph getting scheduled on one of the nodes. And like, that's 140,000 packets per second. Who's still doing 140,000 UDP packets per second? Most of the services were never doing that much. And it turned out that there was one service that was doing this. statsd is a UDP-based monitoring stack, and it's many, many, many small UDP packets. And that's a lot of packet overhead that has to go through all those steps that we talked about. And it turns out there was only 4 senders and 1 receiver in this stack, but they were relatively high performance. It was a 4 Java pods receiving a bunch of RPC requests, doing their Java thing, but the statsd stack in this app was sending 1 or even more UDP packets for every single user request. And so it was a lot. And it was basically a load test. It was a huge stream. But since it was only 4 streams, there's 8 queues, there's a big load imbalance on the node. And so that 140K packets was not evenly distributed between the 140,000 requests per second of UDP packets was not being evenly balanced across the available CPUs. And so that led to a lot of contention on that machine.
Yes.
And so now we're going to talk a bit about sessions. So we have a service called Session. Well, what does that do? Well, it just basically manages the cookies. And this is what makes sure that your request is session validated and can go to an actual backend to respond and show you your shit posting.
Yep.
And then, but this service is quite sensitive because it is in the hot path. Every request has to get also validated by the session service. And so we have very tight SLOs on this service to make sure that we are never being slow with the session service, which would make the rest of the requests slow.
Yes. Which also was then the case that team got paged most of the time when something went wrong. So here's how this looked. We have here 8 CPUs, pretty high loaded, at some point 1 completely overloading, no longer being able to keep up. This is the same thing looking at the softnet backlog. So if there are too many packets coming in, the kernel prefers getting them back from the NIC instead of processing them. On a healthy machine, we were doing, I think, 150,000 packets per second per core. So these 15,000 packets is already 100 millisecond of latency before you even start hitting the pod. So we were out of SLO long before we even could start doing anything useful with that traffic. So what has happened there? We got a node with actually 16 session pods on them. How does that happen? We do have traffic that over the day fluctuates. And when we're scaling up, when the service goes up in usage, the horizontal pod autoscaler kicks in, scales up the pods. But as that happens, the cluster fills up, so you need to provision new nodes. So the cluster autoscaler kicks in and gives you new nodes that then get filled up just with a single workload. So by default, if you're running an HPA and a cluster autoscaler and you're not careful, you end up with single tenant machines. We had all cores pinned, with the static CPU placement. We will go into that in a second.
Guaranteed QoS?
Yeah, guaranteed QoS, static CPU placement. We will go into that in a second. And we actually had configured this max backlog to something way larger than 1,000. 1,000 is the modern kernel default. It was done actually for these UDP monitoring setups so that we never lose packets, and it's not that much of a problem on a normal machine where your cost of processing is lower per packet. So because we have such a high cost in our Kubernetes networking, it started to become a problem there. Pinned CPUs. So you can set the CPU manager in Kubernetes to give you static placement of your pods. What that means, if you go in and say, I have a request of 5 CPUs and a limit of 5 CPUs, it will look at your cores and slice out a subset of consecutive CPUs as much as possible, sharing cores so that you're not getting anything from others due to hyperthreading. If you look at that, we're running 96 CPU machines, 48 cores. You end up that, depending on how you pack that, you have 40 to 48 of your physical cores occupied with session workloads, which...
And so when CPU pinning is in place, your process is on the CPU, and all other processes are kicked off that CPU. Yeah. And so you have very nice isolation of your workload from every other workload. And this sounds like a really great idea.
Yes. But then, where would we actually put our network processing? We still need another 8 cores to actually process the network traffic, as we have seen. And we are basically out of cores. We also need to run DNS somewhere, kubeproxy, a whole bunch of other services that need to go somewhere, but we're basically blocking the whole machine for other purposes. And the last one is that you can see here that we have an odd number of CPUs requested. So you still have this one trailing CPU on a hyperthread, where you might get noise from another workload taking some of your CPU. And with that, we can actually go to a really interesting related case. So one day I was looking for outliers in that session because it was often being the problem. I looked it up. I found this as like the top, I think, 5 or 10 session CPU usages, and there was one that's like at 3.4 CPUs used. I was like, great, I have a CPU outlier. I can go to the machine and actually dump the mapping to the CPUs and cores. So I did that, went to the machine. These were the actual CPUs used by that. I went back to my node exporter and said, okay, what's happening on these CPUs? And like first core, one of the hyperthreads was 40% occupied with soft IRQ. Next one, same story. One of the hyperthreads, 40% occupied with soft IRQ. And on the last one, I got lucky again, 40% soft IRQ. So while we were limiting our service to 5 CPUs, what we actually got is like 3.8 CPUs, because we're already taking 1.2 CPUs just for network processing, potentially for other stuff on that machine. It's not necessarily that this session pod was actually using that. Most of it will have been for other workloads on the same machine. So now the only remaining question is, why do we actually have a CPU outlier with that? Where is that coming from? And if we go back and actually look at the user space usage, you end up with something like 2.2, 2.4 cores. So node exporter is telling me I actually don't have that much CPU space in user space. You can graph that, and I did. And here's like at the top, how much CPU did those cores use in total? How much did we have at the bottom without soft IRQ? And how much is our process actually reporting? And here you can nicely see that the reporting of process time And the reporting of what the cores are doing completely disagrees. We're 40% off. And what's happening here is that these two things get accounted differently. The process time gets accounted when the scheduler comes around and puts something new on the CPU. And it checks like what was running before. And says, okay, there was a session pod running. So that one must have been responsible for the CPU. Even if it got interrupted by a soft error queue, even if it got like paused because network processing was happening. And with that, we have this accounting problem. Another interesting piece here is the service was actually misconfigured. It was configured for 4 GOMAX procs. So it could only ever use 4 CPUs. So what we're also seeing here is an actual estimate of the utilization of these 4. So we had one pod that had a way higher utilization of its Go OS threads because it didn't get CPU regularly. And with that, this pod was actually an outlier also in latencies and error rates. So later on, when some colleagues woke up, they were like, oh, yeah, we have higher error rates here, let's delete that pod. So what was contributing here? For one, we have pinned cores. So like you're sliced and forced to use only the CPUs you were assigned to. No way to like take anything else. The kernel can't move you away. You're stuck with that. We actually had an above average node here. Our normal soft error queue rate was more towards, I think, 20 to 30%. This was a 40% utilization of these cores, which was higher than normal, but like not the worst we have seen. We have earlier seen up to 100%. So it wasn't the worst, but still. And we got really unlucky with our core pick here that those two things actually overlap. But we're running many of these pods, so on some of those, you will get unlucky. And with that, I'll hand it back to you.
Yeah. Next up, we have contract. So in a Kubernetes cluster, why would you use contract? That's for firewalls. Well, basically everything that happens in a Kubernetes cluster with the standard Calico networking has a bunch of connection tracking. There are network policies that tell which pods are allowed to talk to which pods. There is node ports that you want to talk to a node, and you talk to that node port, and it will route you to a service. And all of the and there's load balancer IPs, and tons of Kubernetes networking is actually just software programming of IP tables. And in order to do all that, it has to use these connection tracking tables in IP tables. And so there's a thing called netfilter contract, and as a node is running, there are a lot of open connections.
Yes.
And it's a fast path. It's all done with a lot of network address translation. And this is a highly important table that it needs to be fast.
Yeah.
Come on, click.
Yeah.
There we go.
Yes. Yeah, so what we were seeing is that this graph here shows the number of nodes that were at or above 90% utilization of their connection tracking table. And we saw that slowly growing over the course of a week, up to the point that we actually started having connection issues. You see them even if you're below 100% utilization, because you don't really see the micro spikes that happen over time. So even though there were still a few spots left, we started seeing connection issues and things started breaking down. So what has happened in that case? We were running a Kubernetes update, including the underlying AMIs. We wanted to get to a newer version, which is always something you have to do. That one had a new setting in there saying, hey, 1 million connection tracking entries is enough. We were usually configuring it, I think, at 15 million, something like that. And we were doing a Kubernetes upgrade, updating all the nodes. And then we had a kubeproxy bug that we were hitting. We were updating kubeproxy. And for us, we're usually configuring the setting with kubeproxy, basically because it has a flag to scale it based on the number of cores that you have. Because the higher the number of cores, the more workloads you can pack on a machine, and the less caching you usually have on your CPU. So you actually want that to be scaled with the number of cores that you have. And with that, we actually had this 1 week build up because we were immediately running into the issue, but then resetting the value again, and then going through a slow replacement of nodes as we scale up and scale down regularly, which was a fun one to see. So now what? We've done a few incidents, a few problems. What can we actually do about it? Contract. For one, we actually managed to cut our connections by more than 50%. Part of that is that we were recycling or terminating connections every 5 minutes. That's super helpful if you have services that get deployed quickly, that get moved around a lot. It helps to keep these connections fresh and to rebalance all your workloads. But as connections get closed, we need to keep track of them. And according to the TCP RFC, for 2 times the maximum segment lifecycle, which turns then out to be 2 minutes. So for every connection that has a lifecycle of 5 minutes, we actually have to keep it for 2 minutes, which adds a lot of overhead in that tracking. And that's not even going into other reasons why your connection might terminate earlier. We had another thing that we had a really big cross-product of connections. Anton has written a nice blog post about it, the TLDR being the
gRPC.
Yes. If you're doing client-side load balancing with gRPC and your source service is large and your target service is pretty large, you end up with a really, really huge cross-product.
Millions and millions of cross-product TCP sockets.
Yes. And you would also want to check that and see how many requests do you actually do per connection that you have. Because you can quickly run into problems that you're spending more time and cost on opening connections than actually getting requests over the wire. We also added alerting because, of course, you would not want to ever run into that situation again. We said we should never have more than 400,000 connections. That's the point where we would explode the L3 cache of most of our CPUs. And we would want that we allow some nodes to go over it because we have some special workloads where we would still be out of luck otherwise. The session one, we heavily improved the availability. That's like you only see this 1.00 because it's already rounding up. So this is really like 4th, 5th, 9 here. But that big change where it turns out to be close to flat, a large part of that was outlier detection. So as you run many, many pods, your tail quality is often determined by your worst pod in the whole fleet. And if you're running many of those, there's a good chance that you have a really bad one somewhere. So by enabling outlier detection, we got this way, way more stable. The other things is we went through all the settings you could actually do. We removed the limits, so we actually allowed it to go to other cores and use other resources if there is a congestion. We changed the HPA targets. We made sure that the CPU requests and GOMAX procs are actually somewhat in sync. So not saying we request 5 cores and only set our GOMAX procs to 4. And with those changes, we got an additional improvement in our stability. Telegraph.
Yeah, and so what do we do about Telegraph? Well, Telegraph was actually our obsolete monitoring system, and so I simply went into the code for the team that was managing this service, and I pulled my SRE hat out and said, no, let's just delete these statsd lines of code, remove the statsd library from your app, and stop sending statsd packets at all. And yeah, that oddly enough, not only did it, the blue part is the telegraph, and that cut the CPU to basically 0. And it also cut the CPU time of the service itself in half, because it was just it was spending half of its CPU time sending UDP packets for monitoring, because this service had already been converted to our Prometheus monitoring, which is significantly more efficient.
Yes.
And so, yeah, we that fixed the CPU overload for those UDP packets, and that service was now happy.
Yes, but like, what can we do overall for this CPU load? So one of the things earlier said is like we're fetching the packets and put them onto the softnet backlog on the corresponding CPU. You can reconfigure that and say, please look again at the package, hash it again, and put it onto different CPUs for processing. In that case, the second hashing is actually aware of all encapsulations. So it will do multiple rounds, look into all the encapsulations until it actually figures out where the stream needs to go and hashes based off that. So it fixes both the imbalances that we were seeing and it spreads out the load. This is called receive packet steering. There are equivalents also for sending packets. And we have enabled that in production. Here's a machine that started off with something like 80% utilization on 8 cores. And you can later on see how we're below 40% for all the cores. The IRQ cores are still a bit more occupied. We might want to still configure how we're batching IRQs and packets when we receive them. And the processing is below 20%, even for a node where before the change we had really, really high CPU usage. We're also now seeing that going up over time as people discover that they can actually start using more CPU and more networking with that. The accounting delta that we were seeing, similarly, there is a way to change how this is happening. One way is threaded IRQs. You can force all your soft IRQ work to be done as kernel threads, or you can enable IRQ time accounting in the kernel config. Both things will change that. We're still debating if we should do this, because it will change all our metrics. It will change behavior of the HPAs especially, which is a rather annoying change. And there's still people debating which of the two settings is better. As we've seen, this setting that you misaccounted gives you a better overview of the actual utilization of your threads, whereas the other side gives you correct accounting.
But you will no longer have soft IRQ time accounted to the user space process. And this is good and bad. Which is the right thing to do, we don't know yet.
The thing that's a bit worrisome about it is that this CPU process time is also how the kernel discovers how to do fairness between processes. So, and like how to pause you if you run over your quota and things like that. If you all of a sudden get 40% occupied by something else, what are we even doing there? The last one, actually our CPU cost. We did a nice flame graph. We checked like what are we actually spending our time on in these soft IRQs. And it turns out that we're mostly talking about IP tables here. So basically all the time we're spending in there, there's the small one where you don't see any of that pink. That's where the actual transmits and receives happen, but the rest is really about IP tables. And we're talking about more than 4,000 cores here. We did a comparison with an eBPF plane with Cilium, and it cuts the cost in half overall. So yeah.
And yeah, this is not just our effort. This is quite a number of different teams, whether it's our traffic and transport team, our compute team that manages our Kubernetes clusters, and the application teams also got involved to help debug these problems. And it was a really great collaborative work between a bunch of different teams. Yeah. And so, thank you.